Right, we're now going to have a look at the different types of enthalpy changes. Now, if you remember, when we're talking about enthalpy change, we give it this symbol here. So it's a delta H, like so. Okay, and enthalpy change is usually has the units kilojoules per mole, so mole to the -1. So enthalpy change tends to have those units there. Now, as you can imagine, when we do calculate these enthalpy changes, it can differ based on the conditions we do it under. So what chemists have done is they've come up with a set of standard conditions that we always use when we measure enthalpy changes. If we've done something under standard conditions, we tend to give it this symbol here, which is, it kind of looks like the underground sign. So it's a circle with a line going through it like that. Okay, so in terms of the standard conditions, you need to know them because you can be asked to state them in an exam. So the standard pressure is 100 kilopascals. You may see it being written as 101 kilopascals sometimes, or you can see it as 1 atmosphere. All of those would be accepted in the exam, but it is technically 100 kilopascals. The standard temperature is 298 Kelvin, which in degrees Celsius is 25 degrees Celsius. So again, that would be allowed in the exam as well. Either of those would be fine. If we're doing something with solutions, the standard concentration of the solution must be 1 mole per decimeter cubed. Everything must also be in its standard state, and you'll see that in the definitions. All reactants and products must be in their standard state. So what that means is that substance at room temperature and pressure, what state would it be? And that's the state symbol you should use. So for example, if we're talking about water, water under those standard conditions at room temperature and pressure is going to be liquid. So we should give it the liquid state symbol and not any other. Right, let's now have a look at the first one. So you do need to know these definitions, and these are usually about 3 marks in an exam. So all these definitions can be split up into 3 sections, and I will explain that in a second. So this one here is the standard enthalpy change of reaction. So when we're talking about this one, so it's still enthalpy change like this, but because we're talking about enthalpy change of reaction now, we put a subscript R between the delta and the H, and if it's, as I said, it's standard enthalpy, so it's done in a standard condition, so we give it that standard sign as well. Okay, so in terms of marks, this one's split up into 3. So the first mark would be enthalpy change that accompanies a reaction. The second mark, and I say the most important one, which you need to apply to the actual equation, is that it must be the reaction in the molar quantities shown in the chemical equation. Okay, so it must match the molar quantities shown in the chemical equation. And then everything, so the last mark is everything must be done in standard conditions with all reactants and products in their standard states. So let's just do an example of that. I'm just going to do a reaction here, and I'm just going to make up the enthalpy change for it. So I'm using calcium carbonate, which is solid under standard conditions, and let's just do the decomposition of that. Okay. So let's say that I looked in a data book and I saw that the enthalpy change of reaction for this under standard conditions is positive 100 kilojoules per mole. Okay, you don't need to know these numbers at all. They will be given to the exam if you're expected to use them. But in terms of this definition, this value here matches the molar quantities in this equation here. Okay, if I were to change the molar quantity, so let's imagine that I doubled everything here, so I put balancing numbers, so I put 2 in front of everything, it's still a correct equation, okay, because it is still a balanced equation, but now it doesn't match that enthalpy change of reaction value here. Okay, so bear that in mind, the value you get here actually matches the equation in those molar quantities. Okay, so this one over here does not now match this equation here. Okay, let's move on to the next one. So this is now standard enthalpy change of formation. So the symbol for this one, so again, delta H, but because it's standard enthalpy change of formation, I now put a subscript F. It's still standard, so still has a standard sign. Right, so again, usually 3 marks. So it's the enthalpy change that takes place when 1 mole of a compound, and this is the important part, 1 mole of a compound is formed from its elements. And again, under standard conditions with all reactants and products in their standard state. So the important part here is that 1 mole of a compound is formed from its elements. So let's do an example of that. So let's do the formation of magnesium oxide. So magnesium standard state is solid, oxygen is gas. Oh, sorry. And that goes to MgO. And that's going to be solid in its standard state. Okay. The important part here when you write the equation for this is that you are forming 1 mole of the compound. So that means you shouldn't have a balancing number in front of this. Okay, so when I balance it, I've got to make sure that there's just 1 mole of my compound. So that means I'm going to make this into a half to make that right. And therefore, let's just again write a value for this one. So let's say that this one is minus 600. Ooh, minus 600 kilojoules per mole. Like so. Okay. Now, as I said, this value only applies if I'm making 1 mole here. If I were to have doubled this equation, so imagine if I put 2 here, nothing here, and a 2 here, this would be the incorrect equation and it wouldn't match the definition. So it wouldn't be the standard enthalpy change of formation equation for magnesium oxide. Right, next one is the standard enthalpy change of combustion. So essentially we are burning something, and this one here is going to have this symbol here. So I'm going to have a subscript C, and again, because it's standard, I'm going to have the standard symbol there. So this one is the enthalpy change that takes place when 1 mole of a substance completely reacts with oxygen. So when it says completely react, it's got to be complete combustion, so excess oxygen. But the important part here is that it's 1 mole of a substance. Okay, so now when we're writing out the equation, so let's just burn some methane. So that's going to be gas. So as I said, it's complete combustion. So if I'm doing complete combustion of hydrocarbons, I must form carbon dioxide. Oh, sorry, what's happening there? And everything must be in its standard state like so. Okay, so when it comes to balancing this, I've got to make sure that I only have 1 mole of my substance. So I shouldn't have a balancing number in front of here. Okay, so if I now balance that, I need to have 2 waters and 2 oxygen. So that's fine. I've still got 1 mole of that. Okay, so that's the important part of enthalpy change of combustion. You have 1 mole of the substance burning. You shouldn't have a balancing number in front of that. Enthalpy change of combustion is probably always going to be, not probably, it definitely will always be an exothermic reaction. So the enthalpy change for this one is going to have a negative sign. So it should be a negative enthalpy change of combustion. Okay, and last but not least, this is now the standard enthalpy change of neutralisation. So in terms of symbols, I'm going to just do it down here. This one we write neut here, and everything else is the same. Okay, so this is now the enthalpy change that accompanies the reaction of an acid by a base, so an acid with a base. And the important part here is that you form 1 mole of water. And again, everything standard conditions with all reactants and products in their standard state. So essentially, all of these, so remember all acids reacting with bases are going to have this ionic equation here. And you always need to form 1 mole of water. So make sure you balance it so you are forming 1 mole of water. And if you do this, you should actually find, because given that they all have that same ionic equation forming that 1 mole of water, you'll actually find that all of them will have a value of, close to minus 57 kilojoules per mole. So this is probably the only one that's worth remembering in terms of numbers to memorize. And you are going to do a practical with this as well, where you should get a value close to minus 57 kilojoules per mole.